welcome back, and we're pleased to have the second talk of the morning session from Siampos from Aristotle University of Thessaloniki, who's going to tell us about scale without conformal invariance from integrable deformations of coset CFTs.
Okay, good morning to everyone. First, thank the organizers for putting up this nice workshop and for inviting me to give a talk here. So, as Ben said, I'm going to talk about some deformations of integrable of coset CFTs, which preserve integrability. And as we will see, this kind of deformations will preserve also scale, but not conformal invariance. So let us start. Imagine that we have a field theory. So in a field theory, once you start doing loops, you will encounter counter terms, and the quantum behavior of this theory will be encaptured. One of the things that will be encaptured, apart from animal dimensions, will be the beta function. So how the couplings change with energy parameter. So usually this is done. This is done perturbatively, order by order in the parameters. And this is a parameter here, lambda. And usually we start from the free point, the Gaussian point. It's getting quite cumbersome to go order by order and derive one loop, two loop expressions. So the question that we like to ask, and in a simple example, we'd like to derive, if possible, and the question is it possible to derive an all loop beta function? All loop, I mean, in the couplings, for example, here, the lambda. Another question is, imagine that this hadn't been done, so we start from the Gaussian point, we perturb order by order. The question is, can we find a no-loop effective action? So an action that can have some kind of one loop beta function, which will capture this one. Why that one? Because the goal is that if we have the all-loop beta function, we can uncover non-perturbable symmetries. We can also find non-trivial fixed points towards VIR. Here, for example, I consider that I start from a fixed point in the UV where the coupling is 0. And another question that we'll ask here is that can we find fixed points which preserve scale but not conformal invariance? I will explain that later on. We'll start with these simple aspects in a two-dimensional field theory, namely the non-abelian theory model. Okay. So the main points of this talk, first I'm going to introduce the model, then I'm going to introduce its effective action. Then we'll start with the simplest example, which is a two-dimensional example. Two-dimensional, I mean, in the what's going to be with two fields, still two-dimensional field theory. And we're going to raise the issue of scale invariance. Then we're going to consider supergravity embeddings of this model. Then move on to higher dimensional cases and to the recent work with George issues. And then we're going to conclude. So start with the model. So the starting point, instead of starting here with the Gaussian 3-point, we'll start from a field theory. And the field theory, we're going to take the Weisel-Miller-Witten action at level K, and for a group element G belonging to a semi-simple group. So this is the kinetic term, and this is the Weisel-Miller term. This is invariant under the left-right current algebra symmetry. So this is my starting point. This is my conformal field theory. And what I'm going to do is I'm going to start with this field theory, and I'm going to perturb it using this current bilinear. This is an operator which classically before turn on the perturbation has dimension 1,1, and the deformation parameter here is this lambda b. K is the level of the Weisel-Miller-Witten model. The J's, the J plus and the J minus, are given in terms of a pullback version of the Moret-Cartan forms on the worldsheet, and they satisfy, for example, for the J's after analytic continuation, we satisfy this current algebra at level K. Okay, so this is, so I'm going to start from the Gaussian model. I'm going to perturb. So let us see some properties of a non-abelian tilde model before we start. There was some works by Kutashov in '89 where he found, doing a no-loop computation or loop in the deformation parameter lambda, where he took the matrix here to be isotropic, but leading order in 1 over k, and k being the level of the current algebra, so something's simplified, but the beta function is given by this expression. This is the quadratic Casimir of my group G. And mu is the energy scale. On top of that, in another paper, using path integral arguments, he found that what should be the effective action, if such exists, it should capture some kind of Weak-Storm duality. So if I take my lambda to go to lambda inverse and k to minus k, and for large value of k, this should be a symmetry. It can be seen, it's rather trivial, but this is a symmetry also of this beta function. Okay, so this was done by Kutashov using again all loop perturbation, doing perturbation, conformal perturbation, order by order, and resumming the series, and using path integral techniques. Still, what we know here is that at this level, we have the conformal point plus the perturbation. And the question is, can we construct an effective action? Is it possible to construct such effective action which will have the beta function visual and the symmetry? Let's see, before moving on. So, some years ago, around more than a decade, Kostas Fetsos derived an action which has this form by following a gauging procedure, which is the Weismann-Witten model, and this kind of deformation, where you can say J plus here and J minus, but apart from the lambda, the matrix lambda, there is on top of that the matrix D. The matrix D is the adjoint action going from the right to left, and you can map the right to left molecular transforms. This was done for a general semi-simple group. Some years ago, more than 20 years ago, there was some kind of brute force approach by this gentleman, but only for the SU2 case. So some properties. This action, as you can see, as it can be seen, it has some kind some algebra, has an explicit Weak-Storm duality. And what I mean by that, I mean at this level, I have my parameters is the group element, the level, and the coupling. If I take the level formally, so that the parameter space I have kappa and lambda, and take lambda to lambda inverse and k to minus k, and the g to g inverse, this is a symmetry of the action. The second thing is that if I take lambda to go close to 0, you can see that this then, in a sense, it becomes very, very large. So it's significantly larger with respect to that. So I can neglect that one. So I get the starting point. And for lambda equals 0, if I strictly set lambda equals 0, I will get the Weismann-Witten model. Okay, so one point that's in agreement with the works of Kutashov at first is that I have an explicit Weak-Storm duality. Of course, this is not, I cannot name it still at this level of effective action. Another property is that as lambda goes to 1, the limit is a bit singular, and one has to take also zoom in. The g goes to 1 in a related way, like that. And what we'll find is what is known the non-abelian dual model of underlying principal chiral model, and where the coupling matrix is epsilon, and it's here. Okay, this is a sigma model, so this is a two-dimensional field theory, and going back here, I can write the fields in this indicated form. So if I expand my parameters like that, TAR my generators, my group generators, if I do something like that, the group element, then the action formally, that is only for notation, light coordinates takes this form, xn's, x are this one. So this is the G and the B, so this is the metric of my target space time, and this is the corresponding to form. So starting from this point, in this work, the extended previous works by Friedan, and what they found is that the one loop beta function of this generic model takes this form here. In terms, R mu is the Ricci scalar of this guy. H is just the field strength, the corresponding field strength of B mu here. And on top of that, there are this kind of additional terms, psi. These are called, there are two names, either diffeomorphisms at the level of the metric, or some filter definitions. So by using this approach, we're able to find the beta function. This beta function, however, as I told you, this is an one loop, and the corresponding one loop here, the corresponding alpha prime that we have, is 1 over k. So alpha prime has a very, very small, so we can trust this order. So k must be much larger than 1, and we derive a one loop beta function. Again, one loop in the k expansion, or in the one of the k expansion. Assuming that the CG is positive at this level, have in mind, for example, cases like SU2 or SU2, SO2 or whatever, SO3 and higher, then we can see that if lambda goes to 0, this is a fixed point, okay, and since this is negative, the theory will flow from the UV, whereas the Weismann-Witten model, towards the IR, whereas the non-abelian dual model. On top of that, as we said, this expression matches the all-loop beta function found by Kutashov. Okay? So this is another point why I name this the effective action of the Turing model. So other properties is that this is classical integral. So if I take this model per se, and I consider specific values for the matrix lambda V, like for example, the isotropic case, or the cases like the symmetric concept, then one can rewrite the equations of motion in terms of a Lax connection. On top of that, the charges that we are going to find by the monotropy matrix, one can even show that these charges are in involution. One can even play the same game for the lambda deformed SU2 case for the isotropic. Even for the lambda deformed Jack-Baxter model, where you deform not just the isotropic case, but you deform what's called the Jack-Baxter sigma model found by Klinchik. And then even for other cases, which extend the symmetrical sets, in the work by them. Okay. Are there any questions till now? This is just the setup. And I'm going to explain how this works in two particular examples. Okay. Let us start with the simplest case. So I start with a lambda deformed SL2R over SO2, non-compact cosette CFT, where in terms of the previous language, the lambda AB takes the form, the diagonal, the 3 by 3 matrix, lambda, and 1. 1 is used here, so I can get the cosette, so I get it fixed. So the action, the corresponding action, takes this form which is here. And on top of that, I have a scalar, which is given by this expression, phi being the logarithm of the hyperbolic sinus. This model is classical integral, and the charts are involution. Okay, this was, one can follow the results from here, or can even do it explicitly for this case. It is also normalizable at one loop order in the 1 over k expansion. Here it's much simpler. This is just a two-dimensional target space. There is no B field. And here, the energy flow is just very scalar plus very derivative, the diffeomorphism. Psi is not given, but it takes this very simple form, being the gradient of my scalar here. And one can find that the beta function is much simpler here. This is the coset case, it's not the group case. It takes this form, where the K, the flow, the level of energy with the model does not flow. So it does not change with respect to the parameter. So the right scale. So some properties of a beta function. This beta function is linear or lambda, and the operator which drives the perturbation is relevant. So the dimension here, K is positive, is bigger than 0. It respects explicitly the Wickstrom duality, and also an additional symmetry where I take lambda to go to minus lambda, and this kind of shift here. At this level, this is imaginary, but it's also symmetry at the level of the beta function. I can integrate the energy flow, and one can find easily this very easy expression. But in the IR is when lambda equals to 0, and the UV is as lambda equals to 1. Okay. More properties. In the IR explicitly, we have the starting point, vessel to R over SO2 gate Witten. This is the action, and this is the dilaton. Note a crucial property, a property that will come now crucial in a bit. Here, this is trivial to see, but this has a shift symmetry, going tau here to tau plus C, C being a constant. So in other terms, partial tau is a Killing vector of his background. Towards the ultraviolet, as lambda goes to 1, we can take this limit, but we have to rescale the rho and the tau in the previous expression in order to make sense. And what we obtain is the non-ability dual model of this Price-Parkara model. Although we did this limit at the level of the action, one can find also that the energy flow is in agreement using some kind of complicated deformulas. Okay, moving now to the main topic of this talk. So scale invariance. Let us again consider the action that we just showed to you 3 slides ago. So start with this action. And here tau is a non-compact variable. So I take this asymptotic like limit. So I shift tau with a very large number, minus 1/2 logarithm of epsilon. And I scale lambda by going like epsilon times lambda, with epsilon going to 0. So here, after doing this limit, the limit makes sense, and it is constructed in order to make sense. And one finds this action. The first part here, this is the part here, this is the gate Witten model. So this is innocent at the level of a conformal point. This is symmetry. However, here, when lambda is different than 0, this ceases to be a symmetry, and there is an explicit dependence. Nevertheless, in this case, one can see that lambda here drastically simplifies, because in a sense, lambda going to 0 here. And the only lambda dependence is linear in lambda. Properties. As I told you, partial T is a Killing vector when lambda goes to 0. So I can freely shift tau. However, for any value of lambda different than 0 at this action, one can absorb any value of lambda being different than 0 in a shift of tau. So this should have some kind of consequences that we'll see in the next slide. This model is classical integral in charge involution. This is inherited by the parental model. I just made this kind of limit. And the corresponding target space-time, one can see that it's a black hole. This is a black hole beyond the singularity, so extending the result of Witten for the first part. So the model here, let's study its normalizability. So the model here is normalizable at one loop, as I told you, in 1/k. This is my alpha prime, and the energy flow of this parameter is given by 1 minus C lambda over k. What is C? Let's see. Psi, the psi that I said previously, this is just filter definitions, but I'm allowed to do in a field theory when I'm studying its normalizability. Is given in terms of a scalar plus the additional vector. And the C here, the red C, this is just partial T. So the parameter lambda, as we said previously, it can be absorbed in a shift of tau. So I can freely pick for lambda different than 0, the value lambda equals to 1, if lambda is different than 0. So this model, this is very puzzling behavior because we have a beta function, which beta function depends on an arbitrary parameter. And this is unphysical because this just reflects the definition. So these models are called, this model is called a scale invariant when lambda different from 0 because the corresponding diffeomorphism, this is the vector. So if I write with respect to the form, this cannot be written in terms of a derivative of a scalar. This goes along to the works of Hull and Townsend. However, at this point, one might be worried because we're in a two-dimensional field theory. In a two-dimensional field theory, there is a no-go, famous no-go by Olszynski, going back in '88, which says that in a two-dimensional field theory, with a compact target spacetime, and admitting that it's unitary, one can show that scale invariance implies conformal invariance. In this case, we avoid this kind of theorem because our target spacetime is not compact. Scale invariance does not, of course, this is not just in two-dimensional cases. There are also scale invariance also in the standard electromagnetism when D is different than 4 is there. So scale does not imply conformal invariance except in 4 dimensions and in a standard, more or less, QFT language, field theory language, classical field theory. The trace of energy momentum tensor does not admit the form of a double derivative of a symmetric rank 2 tensor. Okay, so for example, electromagnetism in 3 dimensions, this is scale but not conformal invariant. And another, for example, part that we noticed is that the deformation here in this form admits, curiously, it was admits the form that we start from the field theory, we start with this metric, and imagine that the corresponding metric here can be, so the deformation can be, takes the form of what's called it's well known, the Kelsen deformation. It's a deformation of a metric with deformed by a null and geodesic vector. This was found by Kerr and Schild in '65, 2 years after the famous paper of Kerr in '63, deriving the Kerr black holes and drastically simplifies and gives some kind of intuition how one can find the Schwarzschild and the Kerr metrics. And the crucial part was the Kerr, of course, that was found 40 years ago. Still here, in a very different context, scale invariance comes some kind of this kind of deformation for this class of models. So again, we have scale but non-conformal invariance. In addition, this kind of model, this model per se, it can be embedded in the usual type 2A, type 2B supergravity. And for example, as an illustration, it's a non-supersymmetric. The type 2A solution is given by this form. This is the 10-dimensional metric. This is the two aramorph flags. So, however, there is a limit where we can find where conformal invariance is restored. And this limit is when we take the radius rho to be much larger than 1. In this limit, the model drastically simplifies in this expression. And there is a new kind of scalar at the moment, where phi hat is equal to tau. and their corresponding one loop beta function is vanishing. Here, the value invariance is restored asymptotically, and one can rewrite, find some kind of coordinate transformation. But this is equivalent to vessel to R over SO2 cosine CFT. And of course, this rewriting is for lambda different than 0. For lambda equals 0, this is just a scalar times a linear delta. Okay, so we have a model. So we started with our original model, which was a deformation of a cosine CFT. We took this kind of asymptotic-like limit. We found a model which is scaled but non-conforming variance. Still, conforming variance is there, but we have to take this asymptotic limit. There are extensions of this because one can say, okay, this is a very simple example. It might work. This is just a two-dimensional target space-time. So even for high-dimensional cases, just an illustration of a three-dimensional case, one can do some kind of analog zoom-in-like limit, extending a limit found by Ben and Arcadi for lambda equals 0 for this model, and taking this kind of correlated limit. By taking this correlated limit, one can find the corresponding target space metric takes this form, plus the deformation. I wrote the deformation of respect like that because still this takes the form of the Kersel androids. The one loop beta functions, this is the crucial point, takes for this model takes the form 1 minus c. Xi here is the diffeomorphism, plus eta. Eta here is still given by this expression. So at this level, at the level of a metric, one can see, imagine that lambda equals to 0, but if I scale u and v with the same factor, this is a symmetry. It is a symmetry when lambda equals 0. But for lambda different than 0, this ceases to be a symmetry. However, the rescaling here, the analog rescaling, because this describes a rescaling of the same factor, if I rescale lambda and rescale u and v and scale lambda of the same way, this is a symmetry, and this is encapsulated by the C here. So this model is scaled, but non-conformally invariant when lambda different than 0, because I can dial up any value of lambda that I wish if lambda is different than 0. On top of that, this is scaled because the corresponding diffeomorphism, here if I lower the index, this cannot be written as a derivative of a scalar. So following exactly the paper by Harlan Towns. Again, the target space-time here is non-compact. Still, conformal invariance is there, and if I take the coordinate here b to be much larger than 1, one can derive this CFT. For lambda different than 0, and for lambda equals 0, this is just two scalars times a linear delta. So let me say one thing, that for lambda equals 0, one can take this asymptotic limit and a formal T-duality. I mean formal T-duality because there is a symmetry at the level of the metric, but this is not a symmetry at the level of the diloton. One can do this kind of formal T-duality, and one can still find a scale invariant sigma model. However, this is at the point where lambda equals 0. So you start with a CFT. You do this kind of, let me call it forbidden or formal T-duality, and you find this kind of formal scale invariant sigma model. This also extends, and I'm not going to show you, in higher dimensional cosets of orthogonal groups. We have explicitly checked for 3 and 4. And on top of that, scale invariance persists at two loops, so in 1 over k squared, like for example, and we checked it for this case. So the question now, and this is I'm going to one step ahead, is what about cases which are built out of non-orthogonal groups? Can we find analog situations? So can we find cases where we preserve the scale invariance? And will this admit still the Kersel form? So an extension. So let us start now by the lambda deformation of a symmetric coset, the SU3 over SU2. This, for the conformal case, this was done for the non-compact version. by Lugo 94. This was found the gauge was Wiener-Witten model. Here, following this work, we can get fixed value-free model and write like that, H belonging to the U2, and the G takes this form, the G of the coset. My TAs are organized in my group, these are this here, the generators of my SU3 algebra. These are organized in this form, and these here are the German matrices. So I'm taking my lambda AB here, my lambda AB, being, for the case that I would like to go to the coset, being lambda times the four-dimensional identity matrix times plus the four-dimensional identity matrix for the subgroup. If we do something like that, after some algebra, we can find that the corresponding metric here, there is no B field, as there is no B field for symmetrical sets, for the deformations. The corresponding metric takes this form, G bar and G, these are metrics, I'm going to illustrate them in the following slide. And the conformal point, this goes to 0, but lambda equals 0, this is just the metric of the corresponding metric of the gauge was Wiener-Witten model. And there is a scalar given by this expression. The rho here is this kind of radius in this plane, x01, and the g hat and g are rather lengthy. This is the expression, and I'm flashing them out. Okay. So let this, okay, because we don't need them. The model here, what we presented, this is invariant under this kind of symmetries. Lambda goes to lambda inverse and k goes to minus k. And on top of this is quite easy to see just by this rewriting. On top of that, there is an additional symmetry, Z2, another Z2, lambda goes to minus lambda, and this kind of change for x0 and x1, and x0, sorry, this is a type of the other one. And this is normalizable at order 1 over k. This is the algebra flow. And the couplet here goes from the UV, where lambda equals to 0, to the IR, where lambda goes to 1. This model, as lambda goes to 1, flows to the non-abelian dual model of the corresponding CP2 here, the geometric coset SU3 over U2. If we take now the limit, because tau goes to I tau and k goes to minus k, well, what we are going to find, we're going to find a lambda deformation of Lugo model, this SU2 over U1 over U2.
Excuse me.
Yeah, please.
A bit of a naive question, but it doesn't look like the RG flow has a fixed point and lambda goes to 1. So why is that?
The fixed point is at lambda goes to 0. At lambda goes to 1, the model flows towards the strongly coupled part. So it does not have a fixed point.
Why doesn't it keep flowing past 1?
Why?
Why doesn't it keep flowing past 1? Or is that not the right way of thinking?
Because here we take k being positive. So if it goes beyond, if you like, the signature and the metric will change sign. Okay. So, and strictly speaking, if you take lambda goes to 1, this blows up. One should take this kind of zooming limit. Okay. So it's not a fixed point in a sense. There are generalizations, not in this context, with group cases, where there is an additional fixed point going from the UV to the IR. But for this kind of generalizations, you don't need, so this is just a technical comment, you don't need just 1K, you need 2 Ks, one for the left, one for the right side. Here, this just the model flows towards the strongly coupled part, the IR, where you have the non-abelian dual model of the perspective model. Okay, so it's not a fixed point. So if we take tau goes to I tau, we take this analytic continuation, we get this model. Okay. We're getting this model because we're getting this about scaling variance. We would like to have a non-compact target space time. So still, if we take this model and we take the limit, just the limit on top of that, the tau goes to much larger than 1. The metric still takes this form. This is the corresponding scalar. G hat is given, you can see it's much simpler with respect to the expression that I showed you previously. There is a much lengthier expression for the GNU, division and appendix. And if we go, take lambda goes to 0, the space-time drastically simplifies after rotating x0 and x1 to theta and phi, and take the form of a cosine shifty on SU2 times U over U1 times a scalar phi times a linear dilaton. Okay. I didn't do anything in my field in my theory. I just made some kind of asymptotic limit. So the central charge should be the same, lambda equals to 0. And this is rewritten in the following way. This is the central charge of my cosine shifty times plus the central charge of my linear dilaton plus the free scalar. Still, it's the central charge of the starting model. As lambda now goes to 1, this is a singular limit and requires a zoom-in limit. And one can find this kind of length expression where the RT flow of the parameter kappa square takes this form. Okay, this is the asymptotic limit. The asymptotic limit can be embedded in type 2 supergravity. What we have found till now, we have found three kinds of two kinds of embeddings. Only for lambda equals 0 at the conformal point, and only when lambda going to 1. At lambda equals 0, you find three embeddings. The first one is in a type 2 solution, where the 10-dimensional matrix takes this form, ADS 3 times and 3 times M4. M4 is my metric at lambda equals to 0. There is a free flux, the free form here, and there is no Ramond flux here, so this is why we will call it type 2, not type 2A, type 2B. And this is the dilaton. And on top of that, there is a condition between the radii of ADS3, S3, and the K, the analogs, the radius of the M4, this kind of condition. In addition, there are two kinds of type 2A solutions, this ADS4 times S2 times M4, or ADS2 times S4 times M4 with non-trivial other fluxes. They're a bit more lengthier, so I'm not going to present them. They're in the paper. And as at lambda going to 1, there is a type 2A embedding for ADS2 times S4 times M4, where M4 here is this. So, but as I told you, it's not like in the previous case. The embeddings that we found are not for generic values of lambda, these are just for this value here. So what about the scale invariant model? So here again, we start with this non-compact deformation, and we apply the same analytical continuation. So we do this kind of analytical continuation first, and then after that, we take the limit where U is much larger than 1, lambda is much smaller than 1, and lambda going times U, this is finite. Resulting, because lambda goes to 0, resulting to this very simple expression, plus the scalar, and relative that takes this form. So I'd also note some relationships for this for the beta for the scalar and the diminutive. Diminutive bar and diminutive are given by this expression just for illustration. The model here is normalizable at one loop in 1 over k, and the RT flow takes this form. As you can see here, again, it's the same point. Xi is a scalar, given terms of scalar. The standard field plus theta, however, takes this form, and C being constant. This is completely unphysical, as we said in the previous case. Cannot have a beta function depending on C. And the point is that the parameter lambda, if lambda of course is different than 0, can be absorbed any value of the parameter lambda in a scaling of U by taking U to go into U over lambda. So for lambda different than 0, we take C to be minus 3/2, yielding a scale invariant model because the corresponding theta here cannot be written in terms of a scalar. Crucially, well, let's say we notice that the corresponding deformation does not admit the curve form like this was done for all the other cases built out of orthogonal groups. In addition, this model, if we are going to take again the large, going to the asymptotic limit and take x0 and x1 and v much larger than 1 and u much smaller than 1, so this kind of double scale limit, while keeping all this one fixed, one can find a model which preserves conformal invariance. The corresponding metric here drastically simplifies, so this is a metric of a target spacetime, and takes the form of R2,2. This is just a metric. This is corresponding to two scalars. The scalar is y1 and y2, and two linear dilatoms, y0 and y3. In addition, the central charges also match. So let me now conclude. So what I present to you here are lambda deformation for symmetrical sets for basically focusing on non-compact groups. These are classically integral and normalizable at one loop order. And then we present an asymptotic double scale limit of a lambda deformed SM2R over SO2, this example, which preserves scale but non-conformal variance. As I told you, the diffeomorphism here, the reason why I'm scaling scale but non-conformal variance is because at this level, at the level of two-dimensional field theory, the level of the sigma model, the diffeomorphism cannot be written in terms of a scalar. Or, in a more standard field theory language, the corresponding energy momentum tensor. So if I build an energy momentum tensor again, let me go to this point. If I have a field theory which has translational symmetry, the energy momentum tensor is conserved. If it is Lorentz invariant, the energy momentum tensor is symmetric, or can be made symmetric using some kind of improvement techniques. If it is scale invariant, then the trace of the energy momentum tensor should be zero. Or if it's non-zero, then it's the derivative of a scalar, of a vector. This is the virial. If on top of that we have also the full conformal group, then either the corresponding T nu should be traceless or should take this form. This kind of language, this equivalent, instead of checking that, just going with the works of Hall and Townsend to go and find what are the diffeomorphisms. Since the diffeomorphism cannot be written in terms of a scalar, this theory preserves scale but non-conformal invariance. The scale invariant deformation for the orthogonal cases admit the Kershfield form. The target space-time of this case describes a scale invariant black hole. As I told you, this can be embedded in a standard type 2A type 2B supergravity for any value of lambda. Analog extension exists for higher orthogonal groups, dimensional. And then we extended the above results for this case built on based on unitary groups. And the corresponding deformation here preserves scale but non-conformal invariance, but does not admit the Kershfield form. So, an output. So some future questions. So what about scale invariance for higher dimensional unitary groups? This is one could be this on that if this extends. Another question is that it's a bit remarkable that in the orthogonal case, all the deformations that we have checked in higher dimensional cases, all of them admit the Kershfield form. Why this does not happen here? Perhaps there is some kind of extension or Kershfield-like form. Another question is, well, what about scale invariance for non-integrable lava deformations, like when non-symmetrical sets, like for example, this u1, 2 over u1 times u1. In this case, the beta function is not given just by the part which is for the cosets. There's an additional part which is like the group. Does the scale invariance can mimic something like that here? Because it was crucially previously, but the lambda was scaling the same way on both sides. Of course, if it would work, this term would perhaps drop out. Another part is, what about scale invariant models as double scale limits of Young-Baxter models in cosets? As far as we have checked, till now, that scale invariance cannot be found. In the case that playing the same trick and demand scale but non-conformal invariance does not work, and the theory ever trivializes And at the end, we have a flat target space time, and then just conformal variance. And then at the end, perhaps one can either could be this about lambda embeddings of a lambda deformed, the full lambda deformed model, either this one or the non-compact version, in type 2 supergravity, or even in generalized supergravity. That's all. Thank you so much.
Thank you, Kostas, for the nice talk. Questions?
Maybe I missed it, but what exactly do you mean when you have a negative level in your lumino-Witten models? Is it non-unitary or?
No, yeah, reaction is not unitary. Well, the safety, and this is the demands going back to the demands of Polzinski in a two-dimensional field theory. When he said for two-dimensional field theory, scaled results to conformal variance, he had two demands. First, to have to be compact, so plain all around with partial derivatives, and on top of that, to be unitary. So here, both of these cases, these have deformations, but this is why the no-go is avoided.
Yeah, you're using this nice singular limit to get from the group case to the coset, right?
Mm.
So I also, some time ago, I played with this and I figured out that you can also get not only terms which are proportional to epsilon, which vanish, but you can also get terms proportional to 1 over epsilon, which in principle blow up, especially when you calculate 2-loop beta functions or something like this. So do you have a well-defined procedure to keep everything finite there, or is it also something you are encountering?
You mean by saying epsilon, you mean the limit, the non-abelian dual limit?
I mean, you were showing at some point that you can start with a group and then you introduce an epsilon, and when you set epsilon to 0, you naturally go to the coset, right?
So let me. I think you referred to this point here. Let me go here.
Something which was
Yeah,
lambda.
yeah.
Exactly.
You referred to what one?
Well, I think even earlier, right? You had a very simple model, and you were
Yeah,
choosing
exactly.
this lambda, and then you
exactly.
were setting part to
Yeah,
0
then
and part to infinity.
Yeah.
And so in principle, you could get some infinities in your final results, right?
Yeah, but if you do it, for example, you do it carefully. For if let's say you'd like to take the conformal case and you'd like to get lambda going to 0, what you are going to find is you are going to find what the limit makes sense, and you find the coset CFT.
But only at one loop or also at 2 loops? Because at one loop, I agree. At one loop, for some reason,
Sure.
miraculously everything cancels. But then when you start, for example, looking for 2 loop, you might get.
So the action that we have presented, the original action, this is an effective action has some kind of alpha prime, being the 1 over k. So going beyond one loop, this action can have counter terms, and which we have checked in common works with Kostas and works with Ben with Arkady. So there could be counter terms coming up. So the model is well behaved and is stable with respect to the algebraic flows, the model we have described up to one loop. So for large values of k, for subleading k, for subleading factor, one can shoot that counter terms. Okay. Otherwise, the model is not normalizable in a sense, just sticking with this action. One can just check it in the simplest case, just start with the lambda deform SL over O2.
Yeah.
So if you do, this is rather easy to check, and one can play around, and you can see that it's not normalizable. You know what I'm talking about.
Yes. Okay. Thank you.
Sure.
I had a slightly related question, also following on from Lewis's question. So I understand, like when you have the compact case, you flow from the fixed point in the UV to the strongly coupled IR. When you flip it and you're sort of saying that you have a fixed point in the IR, and you have, I don't know what you really have in the UV.
In UV, we're going to have again the non-abelian dual model.
This is not a CFT, so
No, this is not a CFT.
So what does it mean to have this in the UV? I mean, in a quantum, I mean, UV, you expect to flow from some CFT.
Yeah.
you have some strong, I don't know.
Therefore,
I guess my question is broader, is to what extent do you expect all this to make sense at the quantum level, which just sort of follows on a bit of the cloud question as well.
I see your point. Once you go for the non-compact case, you have various problems, like the non-unitarity, for example. So the CFT, what you can trust is at VIR, this is for sure. Going beyond that, but still this is the same comparison. But apart from having the CFT or not the UV, it's not going to be stable until the flows to loop, for example.
Okay, yeah, so. Okay,
Yeah,
so
so it's the same either compact or non-compact in this code. So here what we did is that we start from the formula as we said in the two-dimensional case, the Witten black hole. And the idea is that we'd like to get some kind of asymptotic like limit. And you cannot get something like that in the compact
Sure,
case.
that's fine, yeah.
And the outline, if you like, the corresponding scale environment model, this makes sense. I know not answered your question entirely at this point. So this was some kind of intermediate step to study. We would like to study, for example, asymptotic like limits, both at the conformal point away from that. And on top of that, yeah, with scale invariance. In order to have scale invariance, I cannot get some kind of asymptotic like limit with a compact Tiger space-time. We're going to discuss further.
Yeah. Any other questions? If not, then I think it's time for lunch. Let's thank Kostas again